All right, so once again, 11.6, now we're trying to find the sum of a finite geometric sequence. That means we are working with a geometric series now, okay? So, let's let A sub n be a geometric sequence where to go from one term to the next, we're continually multiplying by the same value, right? Or dividing by the same value, depending on how you want to look at it. And we have the first term A sub 1 with a common ratio R. The sum S sub n of the first n terms of this sequence can be found with the following formula. A sub 1 multiplied by 1 minus R to the power of n over 1 minus R. So you are going to sometimes see it written a little differently. You could distribute this A sub 1 up into the numerator, and you might see it as A sub 1 multiplied by 1 minus R to the power of n all over 1 minus R. Or you could see it like this. This is where the distribution really is. Okay, so ultimately, to use any version of this formula, you need to know the first term of the sequence, you need to know the common ratio R, and you need to know how many terms you are adding up, right? That's what n represents here. Okay, n is number of terms being added together. Okay, and I think it's worth mentioning here, notice we do have a restriction on R. It can't be 0, it can't be 1. That's the same restriction on R for any geometric sequence. Just think if you're multiplying by 0 or you're multiplying by 1, you're not going to get different terms each time. All right, so first example. Let's find the sum of the first 6 terms of the following geometric series. So 3 plus 15 plus 75 plus 375. Okay, so they're telling us it's geometric. So that means there's this common ratio, R. What is it? 5. We know the first term, A sub 1, is 3. And we're trying to add the first 6 terms. So that means n is 6. So the sum of the first 6 terms would be represented with the notation capital letter S sub 6. And that's going to equal A sub 1 value of 3. So I'm going to use the lowest version here. A sub 1 minus A sub 1 times R to the power of n all over 1 minus R. So I'll do A sub 1 value of 3 minus 3 multiplied by my R value of 5 to the 6th power all over 1 minus my R value. Everybody okay so far? All right. Anybody have 5 to the 6th power memorized? It's a pretty large number. Yeah, 15,625. So I've got 3 minus 3 times that, all divided by, that's going to be a negative 4. Okay, now let's multiply that by a 3. So we got 46,875. Okay, so 3 minus that. It's negative 46,872. And we divide that by negative 4. We're getting 11,718. I think we're just adding 6 numbers together, and that sum is pretty large, right? That's because you have a pretty large common ratio here. All right, any questions on that example? Okay, second example. Get that out of the way. Find the sum of the geometric series 6 plus 12 plus 24 plus all the values in between up to 1,536. So notice this is a little bit different than the previous example in that I'm not told how many terms I'm adding together here directly. I need to reason that out, okay? I know the first term and the last term of this sequence that are being added together, so I can use that to reason things out. So let's start, though. A sub 1, that is 6, right? What's R? 2. And then N is unknown here. Okay? So what we're going to have to do to figure out N is we're going to just create the explicit formula for the geometric sequence. And then use that to solve for N, okay? So, geometric sequence. Give me an A sub N. And that's going to equal your first term of 6 multiplied by your common ratio, your R, of 2 raised to the power of N minus 1. Everybody recall that from our previous lesson, right? Okay, now I know the last term here of the sequence that's being added together is 1,536. So I'm going to substitute that in for A sub N. And look what I have now. I have an exponential equation to solve, which we're just coming off of the unit chapter 9 where we were solving these types of equations, right? What's going to be the first step to solve this for N? Divide by 6. Okay, so 1,536 divided by 6. What's that going to give us? 256? Okay. Equals now 2 to the power of N minus 1. Where do we go from here? Luke, you said factor tree? What do you mean by that? Yeah, 2 to what power equals 256? That's ultimately what we want to reason out here. Because if I have an exponential equation where I can write both sides of the equation with the same base, I can then effectively ignore the bases and then set the exponents equal to each other, right? Okay, so what is 256, 2 to what power is 256? 8. Okay, so we'll rewrite this. 2 to the 8th power equals 2 to the power of N minus 1. Now, of course, you probably don't have that memorized, right? That 2 to the 8th is 256. Play around with the values, right? Just test some different powers on 2 until you find what works. Okay, so now we can just set 8 equal to n minus 1, and that means n is 9. So we're adding 9 terms of this associated geometric sequence together. So this sum can be represented with S sub 9. And now we find it the same way we did the last problem. So we'll take our initial value of 6 minus 6 times our R value of 2 to the power of 9 all over 1 minus our R value of 2. All right, so what is 2 to the 9th power? 512. Of course, 1 minus 2 is negative 1. How about 6 times 512? 3,072. 6 minus 3,072. Negative 3,066. And then, of course, that is going to turn positive. You'll know if you're doing things correctly or not, because if you're not, chances are you won't get these to divide out evenly. And I mean, if you're just adding a bunch of integers together, shouldn't the result always be an integer as well? Okay. Questions? All right, example 3. Here we're using summation notation. So let's focus in on this one to the left. We want the sum from 1 to 50 of negative 2 multiplied by 2 to the power of n. Okay, so still need the same values. We need a sub 1, we need our r value, and we need to know the number of terms that are being added together, right? So let's start with the first term, a sub 1 would be negative 2 times 2 to the first power, so that's going to be negative 4. Okay, now to reason out r, let's get a second term here. So if I did a sub 2, that would be negative 2 times 2 to the second power, which is negative 8. So here we can see that r equals 2. Right? And really we should have been able to reason that out from the formula within the sum here. Whatever that number is that's being raised to the power, that's your r value, right? Okay, how many numbers are being added together? So n is 50 then, right? Okay, so this sum is going to equal negative 4, our a sub 1 value, minus negative 4 times our r value of 2 to the power of 50 all over 1 minus r value of 2. All right, 2 to the power of 50. Oh boy, it's giving it to you in scientific notation. 2 to the power of 50. Oh boy, look at that. Four two 624. Did I write that out correctly? Oh, I missed the 9. You're right. How's that look? Okay, now we got to multiply that by 4. How about I do all this at once rather than writing this big long number out again? So let's do -4 plus 4 times that answer divided by, let's see, divided by a -1. Huh. I got something wrong here. Oops. No, I don't. It can be negative. It's a really large value, huh? Let's see. Billion, million, billion, trillion. -4 zillion, right? 503 billion. Zillion, trillion. Yes, I switched it. Trillion, billion, yeah. So -4 zillion, 503 trillion, 599 billion, 629 million, 370,492. Yes. Quite large. Actually quite small, being that it's negative. All right, that's what I get for making up a problem on my own. Yeah. This next one's going to be bad. Let's do this. 10. Is that better? All right, so a sub 3 would be the first number we're adding here. That's going to be 20 times 3 to the second power, right? Or 20 times 9, which is 180. Everybody okay with me plugging 3 in first? Because that's the lower limit this time, right? Okay, what's R? 3. And then what should N be here if we're adding the third term through the 10th term up? 8. Okay. So this sum is going to be 180 minus 180 times 3 to the power of 8 all over 1 minus 3. What is 3 to the 8th power? 6,561. That's all going to be over negative 2. Okay, so then 180 times 6,561. 1,180,000. Like that. All over negative 2. Okay, so then that'll be negative 1,180,800. All over negative 2. What do you get? 5,940. 590,400. Much more manageable.
Just imagine